Hello everyone, so today I will talk to you about the Z-scan characterization technique of third-order nonlinear optical materials. Just a moment, I will use the pointer here. So I will start with a brief introduction. So we know that when we send the light with a high intensity to a center-symmetric transparent material, we get a linear field at omega and a nonlinear field at omega and 3 omega. The linear and the nonlinear polarization is given by this formula. And if we take as a common multiplier the electric field and the permittivity in vacuum, we notice that chi, which is the susceptibility, has changed. Since chi is related to the refractive index with this formula, it means that also the refractive index has changed. This is called the optical Kerr effect. And the final equations of the refractive index and the absorption coefficients are presented here. And we notice that they depend on the intensity. So N2 is the nonlinear refractive index, real part, and beta is the nonlinear absorption coefficient. In order to measure the beta, we use the Z-scan open aperture. So as we see here, we send the laser and we focus to the lens, and then the sample is translated through the beam waist. Of course, high intensity will be in the waist, and any change in the transmission during the translation of the sample will be, of course, due to the nonlinear absorption coefficient, which is beta. A typical figure of the Z-scan open aperture is presented here. As we see, when the sample is far from the beam waist, it's almost constant here. As soon as it approaches the beam waist, we see a decrease in the intensity, which is due to the beta. We can easily fit and extract the beta using this equation here. Next, in order to measure, before we measure the N2, first we need to talk about the self-focusing effect. So when we send an intense beam with a Gaussian profile through the setup, which doesn't have a nonlinear optical material, the focal distance will correspond exactly to the one indicated in the lens. However, if we implement a nonlinear optical material, especially a chi3 material, which has a positive nonlinear optical refraction, self-focusing effect happens and the focal distance will decrease. So in order to measure the N2, which is the nonlinear refractive index real part, we use the closed aperture Z-scan technique. This technique has the same principle of working as the open aperture. However, we add a closed aperture just before the detection. So if you focus with me here in figure A, when the sample is far from the beam waist, nothing specifically happens, and we get the detected value, which is depicted in the red lines. We go to figure B. When the sample approaches the beam waist, self-focusing effect happens, and hence we get a high divergence at the detection, and this is why we get a low transmission, which is shown here. You will see when the sample passes through the focal point, self-focusing effect happens, and instead of getting a divergence in the beam, we get a convergence, and this is why we get a high intensity here. This is all by taking into account that the sample possesses a positive nonlinear refractive index. A typical figure of the closed aperture Z-scan technique is represented here, and we can easily obtain the N2 by using the effect or manually calculating using this formula, where we have all the parameters except N2. Thank you.